Hi, welcome to the workshop of Chem 6161, the first workshop. This is the first question. We have this 6-member ring with a nitrogen and we add BF3, we generate the iminium and then a nucleophile is attacking this iminium. Okay, because this iminium is in a 6-member ring, what we can do is to draw the most stable conformation. We put our eye here, and what we get is the iminium, the CBZ will come to us. I will numerate in order to facilitate. Okay. And then when we have this, I will draw it too. Okay. We can choose going up to draw the half chair or going down. This will give us the two possible half chairs. Okay. Then if we numerate, this is 1, this is 2, this is 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, and we will put the substituents. Okay, in this case, if carbon 6 is going down, okay, the hydrogen will go up, and here we will have the CH2 benzene. Carbon number 5, carbon number 4, and I do exactly the same here. If this is going down, five, and here and the hydrogen. Okay? Here is the two possible conformations. If we analyze the two possible conformations, in this one we have one axial, and this that looks like okay because it's equatorial is crashing a little bit with the CBZ that will be in the same plane. Here we have this equatorial, and this is axial, but is facing away of the CBZ. That means the most stable conformation will be this one. Okay? If this is the most stable conformation, I delete this, and now I am going to analyze how the nucleophile is attacking. I have the nucleophile and the nucleophile following a Burgitz-Dunitz reaction trajectory. Okay, can attack from here or can attack from here. Okay? What we need to analyze? What we need to analyze is how will be the transition state after the addition. That means if attacks from down, what we have is that we have this. Oops. is attacking from the top face, what is happening is that this nitrogen is going down, okay, in order to preserve the tetrahedral environment in this carbon, and we have like a twist bond. However, if we are doing the other one, what is happening is that if the attack is taking place from behind, what is happening is that we are pushing the nitrogen up, and we have something that looks quite similar to a boat, to a chair. Sorry. Okay? That means this will be by far more stable than not this. This will be the favorite approach. This will be the most stable approach, the better approach. Okay? I remove this, and then the only that I need to do is to draw the final configuration. The nitrogen here, the CBZ. Okay, I am not changing any chiral center, and this nucleophile is coming from down. That means that the nucleophile will be like this. This is the final configuration of our compound after the nucleophilic addition. Okay? As a summary, how I did it: first, I draw the most stable conformer in a half shell conformation, always putting the double bond in front. Okay, and then analyze the trajectory of the nucleophile, the one that gives a transition state more similar to a shell. This will be the most stable, and then I get the final configuration. Okay? Good. Then we go for the second one. Second one, we have this compound. Okay, this ester, and then we have here a terbutyl, and here we have a methyl. Then the reaction that we are doing is LDA with ethyl bromide. Okay, first what we need to do is to draw what is happening when we add LDA. Basically what is happening is that we have the enolate, okay, then this enolate is a 6-member ring. That means that we can draw the half chair conformer. Always we put our eye here to see the double bond, and then what I will draw is I will numerate. Always is good to numerate 1, 2, 3, 4, 5, 6. Okay, in order to do this. And as I did before, I draw the two possible half shell, okay, and then one up, okay, and one down. And then what I do is simply putting the substituents. In this case, this is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. In carbon number 5, I have a metal that is going down. That means in this case the metal will be in this direction. Okay, and here will be the hydrogen. In this direction, metal and the hydrogen. And the terbutyl is in carbon number 4, that means it's going up. That means in carbon number 4 I have terbutyl, and here I have the hydrogen, and in this case I have the terbutyl here and the hydrogen here. Okay? Well, in this case it's very easy. Here, in this conformant, I have the two substituents, the terbutyl and the methyl, in the equatorial position, while here both are in axial. Obviously, this will be more stable. Okay, that means that I erase this, I only will place with this. And then remember that it's a nucleophile who is attacking, that means this, the orbital, the pz orbital is attacking, and we have a SN2. Okay, that means that has to be an inverse of the configuration. Inversion of configuration. Okay? The attack will be like this. Not following a Burgitz-Lunitz trajectory, is a 180 degrees, will be perpendicular to the enolate. And now I analyze both trajectories. This one looks quite clean, but this one, when it's approaching, is crashing with this substituent. That means that this will be the preferred approach. Okay, that means that we will have very bad growing. Basically, what I will have is this substituent, terbutyl here, hydrogen, and methyl here. Okay? If I transform this in the normal growing, okay, what I have, ethyl up, terbutyl up, methyl down. And this will be the final configuration of the addition of ethyl group in this position. Okay? Right? Okay then. Then what they are telling us is that we do exactly the same, but with this methyl, instead to be down, now will be up. Okay? How we do it? Exactly the same. That means we have to draw the half chair. One up, one down, and we put the substituents. In this case, the terbutyl is up. I enumerate again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The terbutyl is in carbon 4, that means it's going up. That means that here will be the terbutyl here, hydrogen here, and in this case, in the 4, if the terbutyl is up, terbutyl up, hydrogen hydrogen here. In the 5, we have the methyl up, hydrogen, methyl, hydrogen. Okay? Now the different phenagen conformers will be more similar, but anyway, the terbutyl, the heat substituent, must be in equatorial. That means that this one will be the most stable conformation. That means that I will delete this. And now again, like I did before, I analyze how the nucleophile will come. Again, it's a SN2. Okay. And I analyze the trajectory. And now the problem is that when I analyze this point, this is crashing directly with this metal. While because the terbutyl is in equatorial, this approach looks like more easy. This is why I will take this approach, okay? Because here I crash the metal with the electrophile. Okay, attack. And if I choose this as the approach, what I will get is a very bad growing, but I will get this. Okay, terbutyl, hydrogen. Here will be the ethyl, and here will be the methyl. Okay? And then I transform this in the normal growing. This was up. This was up. And this is down. Okay? This is a difficult example because basically this metal is who is disrupting the approach of the electrophile. But if you justify that this approach is better because you think that this terbutyl is crashing with the electrophile, I also will consider that is a good answer. Okay, even if it's not the right answer, I will consider that is a good answer. The important thing is that you justify why one or the other is the preferred approach. Okay? Good. Then we go for the next one. The next one, basically, they tell us that we have this reaction. We add butyllithium and we get the epoxide. And they ask us why, what is the mechanism? Okay? There are error in the exercise that here, I don't know, ChemGrow put a silicium. Okay, it's a sulfur. If not, will not work. Then basically what is happening is that we have this. When we add the butyllithium, what we are doing is we are forming an ion and we get this compound. Okay? And this basically attacks the carbonyl group, the ketone, we generate this intermediate. Okay, and then this intermediate simply intramolecular reaction. This is a very good given group because it's dimethyl sulfur, and what we get is the final compound. Okay, this is very similar to a Darson reaction. If you are interested in a Darson reaction, I put some examples in my YouTube channel about named reactions, and Darson's is one of them. Okay, you can check it there if you are interested in the Darson reaction. This is a Darson reaction with the Corey-Tchaikovsky reactor. Okay, that's easy. And then they say that we are doing exactly a similar, well, not the same reaction, but very similar. What we are doing is reacting this aldehyde plus this reactant that now we know how it works, butyl lithium, and we want to know which diastereomer of the epoxide we will have. In order to do this, basically what we need to do is to check how is affecting this metal, this chiral center, to the aldehyde. We saw the aldehyde by this phase, okay? And what we have is we have carbonyl group, hydrogen, and then we have here the methyl. Here we have the group that I will say R, and here we have the hydrogen. Then what we need to do is to put the bigger group, because all are carbons. That means that it's not a polar system, it's not a chelation system. That means that we only care about steric hindrance. We put the R group perpendicular to the carbonyl. We have two options. One is and the other will be okay? And then I analyze the nucleophile approach. Remember, the nucleophile has to come from the other side where is the big group, and following a Burger-Dunitz trajectory. Here is crashing with the methyl, here is crashing with the hydrogen. Obviously, this will be more favorable. That means that I can delete this. This is the one that we will use. If we do the addition, what we have is nucleophile, hydrogen, and then hydrogen, methyl. Okay? And then I will draw it. Okay, this center is exactly the same, and then if I choose this center, I get the wedge inside and the nucleophile in this side. Okay, if I am doing it right, I hope that is right, yes, I guess so. Okay, then I substitute the nucleophile by CH2 is positive. Here is the alkoxide, and then intramolecular, that is not chiral anymore. That means this position is not chiral. It's not a stereocenter,